Okay, so the temperature, right, is in the denominator instead of the numerator. So that means the higher the temperature term, so as temperature uh, goes to very large numbers or infinity, if you prefer, right, this term is going to become 0. And the exponential term will become e to the 0th will become 1. So what that means then again, and then we're left with the situation again where the rate constant is going to be equal to the pre-exponential term a. And so we're left, so what that tells us then is that as the temperature increases, right, this will increase the rate constant versus as the temperature decreases, uh, the opposite will happen. The temperature decreases, this becomes larger, and then K starts approaching lower numbers and becomes slower. Another way to think about this is that you have a temperature. Remember, temperature is related to the kinetic energy in the system, all right? But it's a distribution. What it really measures is a weighted average. And so there's a distribution of all the molecules within a system, right, of how much energy those particular molecules have. So at low temperature, a lot of the molecules will have a lower kinetic energy, versus high temperature, more molecules will have higher and higher kinetic energy. Right? So the distribution changes towards higher kinetic energy. Now let's say our activation energy, denoted by delta G double dagger, is here. So that means in order for the reaction to proceed, it has to surmount this kinetic energy. And so only molecules that are underneath the curve in the shaded regions are able to do that in the low temperature regime, which is shown in blue and in shaded blue, and in the high temperature regime is shaded in orange. Okay, so as you can see, there's more area underneath the curve for the orange at the higher temperature. Okay, so that's also what we're measuring. That's another way to think about how temperature increases the kinetic energy of a subset of the molecules within the system, and that allows these molecules to overcome the activation barrier and proceed towards product. All right, so then we go to the pre-exponential term. All right, and so this baked into this is, as you may remember from kinetic gas laws, right? So are the number of collisions, the rate of collisions, how effective a collision is, and that also is what's important to that is the geometry of the collisions, right? So not every collision, when we think about gas laws, right, proceeds to product, because there may be only a certain orientation that the reaction can occur, and so not every collision may be productive, right? So for this, to get a better understanding, we can expand this. So this pre-exponential term, so the terms that are within this are kappa, Kb. So Kb is a constant, that's called the Boltzmann constant. Kappa is the transmission coefficient, which we'll get back to in a second. T is still temperature, and H is Planck's constant. Okay, so we have two constants within this, Kb and H. All right. So within this temperature, okay, again, as temperature increases, right, that's going to increase the rate constant. So that is in the same direction as the temperature term in the exponential term, all right? And then kappa, right, is a probability that if the activation energy, if there's enough energy to overcome the activation energy, kappa is, as the transmission coefficient, is the probability that the reaction will then proceed to product. Okay, so if there's enough activation energy, we can think of, okay, the molecule's at the transition state. Okay, there still may be a chance that it doesn't go to product. All right, at the top of the hill, it may go go to the right and go towards product, or it may go left and go back towards forming the substrate. So kappa is the probability of that going towards product. So what we have then is we see all the influences then on how the rate constant and therefore the rate of the reaction can be influenced, right? So one is, so we have two terms in the exponential term of our equation. that are dependent on activation barrier, which we already talked a lot about for enzymes, and that's what we think about enzymes lowering the activation energy. And then temperature, which we, or as experimentalists, can control, or in physiological terms, the temperature may have a big influence on how the reaction proceeds, or what the rate of the reaction is. Okay. And in the pre-exponential term, again, we see temperature, but then there's also this kappa term, which has a lot of different things baked into it, including the efficiency of a collision, quote unquote, or rather that can be influenced by geometry. And we'll discuss more about how enzymes can affect this kappa term in a later video lecture.